Hello dear learners, welcome to this YouTube channel. You are with teacher Stephen, and today I'm taking you through physics paper 4 to February March 2023. If at all you want to talk to me, you have any challenge, there is my WhatsApp number and my email. You can contact me. So let's go to the first question. The first question is saying a boat crosses a river. The boat points in the right angle to the river bank and it travels at a speed of, so here we have the speed of the boat, which is actually 3.5 meters per second. Then we are having also the river current acts at right angles to the direction of the boat, and the river current has a speed of 2.5 meters per second. By drawing a scale diagram or by calculation, determine the speed and the direction of the boat relative to the river bank. So of course let us let 1 centimeter to represent 1 meter per second. In other words, when you're drawing a scale diagram, let us the speed of the boat, you just measure from here, make sure that it is 3.5, but having it in mind that every 1 centimeter is 1 meter per second. So this is 3.5 centimeters. So make sure that you measure it. Then another one which is going like this. This is supposed to be the river bank, the speed of the river, 2.5 also centimeters. So make sure that you measure this distance. So to know the speed and the direction of the boat, draw this other line here. So this is the direction. Normally when we say direction, we are meaning the angle the speed of the boat is making with the speed of the what? Of the current of the river. So the angle is given as theta. So here, to get a speed, we are going to look for this value. So of course you can measure from here up to here using a ruler. You can measure and just get the what? The distance. So that will be the speed. Or you can use Pythagoras theorem, which is from a squared plus b squared is equal to c squared. Plus b squared is equal to c squared. And then from there, a squared is 2.5 squared, b is 3.5 squared. Then c squared, we can call it resultant speed squared. So when you add this, you're supposed to get 18.5, which is equal to resultant speed squared. So you take the square root both sides. So resultant speed, you'll be able to get 4.30 meters per second. However, I can write it to two significant figures, which is 4.3 meters per second. Again, when you're talking about the direction, you can use trigonometric ratio, whereby you get tan theta is equal to opposite over adjacent, which is equal to, of course, opposite is this side, adjacent is this one, which makes 90 with the theta. So it will be 3.5 divided by 2.5, and that is tan theta. So theta alone equaling to tan inverse of 3.5 over 2.5, and you'll be able to get, when you use your calculator, you're supposed to get 55 degrees. That would be the what? The answer. So you can write it as 55 degrees. So let's continue. So we can go to part B. Speed is a scalar quantity and vector, and velocity is a vector quantity. State the name of one of other quantity and one other vector quantity. So of course, when you talk about scalar quantities, they're the one with the only magnitude or only size but no direction. So examples, we have mass. Mass is a scalar quantity. We have time. We have distance. We have temperature. Mentioned but a few. So we have many, but I've given you that. Then also we can have vector quantity. These are the one with both magnitude and direction. Example, we have acceleration. We have momentum. We have momentum. We have force, etc. Also you can say etc. So there are many, but pick any two from scalar quantity, pick one, vector quantity, pick one, and you'll get your 2 marks. Let us go to another number. Number 2. Figure 2.1 shows a ship loaded with containers. So we have containers loaded on the ship. The ship is made of steel. The density of steel is 7,800 kilograms per meter cubed, and the density of water is 1,000 kilograms per meter cubed. Explain why the ship floats in the water. So you can say that the overall density of a ship is less than the density of water. That's number 1. You can also say that the ship is not a solid steel. You can also say that there are spaces in the ship. All these will explain why the density of the ship finally is less than the density of water. Because you look at the spaces left there. So those spaces, of course, makes the ship light. So its density becomes less, and then it ends up being less dense than water. Also, the ship is not like in a solid form. It is hollow. Meaning that if it is hollow, it will make the total volume to be big, but its mass will be small, hence making it less dense. So let's go to part B. The containers with the greatest mass are loaded near the bottom of the ship. State and explain the effect on the stability of the ship of loading the containers in this way. So let's look at the reason why these containers must be put at the bottom and not on the top, and how does that one help in the stability of the ship. We shall say that the greater the mass, the mass near the bottom, the lower the center, the lower the center of gravity, 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 meaning that in case you put a lot of mass near the bottom or at the bottom, of course the center of gravity becomes low, and once the center of gravity is low, it means that the stability of the ship will increase. So that's it. So when you put many containers at the bottom, you are increasing the mass near the bottom, and yet you are lowering the center of gravity, hence making the ship more stable. Let's go to part C. A crane lifts container 48 meters vertically upwards. The mass of the container is 30,000 kilograms. Calculate the energy transferred to the gravitational potential energy stored in the container. So we are having the height that these masses, the containers move, which is 48 meters. We even have the mass of the container, of which the container is 30,000 kilograms. So they're just asking us for actually we know the G from the beginning. They are demanding us to use G as 9.8. Don't use 10. So we shall look for gravitational potential energy from mass times gravitational field strength times the height. So it should be equaling to 30,000 kilograms times 9.8 times 48, and then we'll be able to get 14111. Use your calculator, you're supposed to get that. So that is 14,112,000, and this is joules. So in two significant figures, we'll have it as, you can have it written like this. So that is 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. Joules. Or you can write it as 1.4 times 10 power 7 times 10 power 7 joules in standard form. Let's go to another number. State the principle of conservation of energy. So the principle states that energy cannot be created, energy cannot be created or destroyed, but can be transformed or changed from one form to another. So that is the principle. Energy cannot be created or destroyed, but can be changed from one form to another form. So that is the principle of conservation of energy. Part B. A wind turbine has a maximum output power of 18 megawatt. The turbine operates at maximum power of 4 hours. Define the unit kilowatt hour. So we can say this is the energy. This is the energy transferred. Energy transferred in one hour at a rate of transfer of 1 kilowatt. So you can find it as that. Roman numeral 2. Calculate the energy produced by a wind turbine operating at maximum power for 4.0 hours. Give your answer in kilowatt hour. So we already know that when I have power, so energy will be equal to power times time. So I have power as 1.8 times 10 power 6, then times the time taken, which is 4 hours. So you'll be able to get 7,200,000 watt hour. But to put it in kilowatt hour, we are going to have it as 7,200. Then you replace the 3 zeros with kilowatt hour. So you write it as 7,200 kilowatt hour. But already it is written there. You might ignore it. It is already written there. So let's go to another number. Radiations from the sun is the main source of energy for most of our energy resources. State 2 energy resources that are not due to radiations from the sun. So of course we have tidal energy. We have geothermal energy. We also have nuclear. All these, they don't get their energy from the sun. Nuclear energy. So let's continue. Number 4. Figure 4.1 shows a metal pan on an elastic hot plate. The pan contains 200 centimeter cubed of water. So they're asking us to state that thermal energy is transferred through the metal pan by conduction. State and explain the 2 ways that thermal energy is conducted in a metal. So number 1, we can say that metals, of course, they are made up of metals are made up of free electrons. Metals are made up of free electrons, and these electrons move through the metal and collide with the atoms of the metal. Which makes them vibrate vibrate, which makes them vibrate and pass heat energy to the next layer of atoms. The process continues because when heat reaches on that next layer of the atom, that layer, those atoms also vibrate and they pass heat energy to another layer. So in that process, heat will move through the metal and it will reach the what? The water. The water boils and leaves the liquid as a gas. Explain in terms of forces and distance between particles why the gas occupies a much greater volume than it does as a liquid. So number one, you can say that the attractive forces between the attractive forces between liquid molecules is much compared to the one in gases. So we see the force of attraction between liquid molecules is bigger or is much compared to the force between the gas molecules. So in other words, there is a bigger intermolecular force between liquid molecules and less in gases. Then another one is that particles in a gas, are much further apart than in liquids, meaning that because particles are far apart from one another, they will have to occupy a bigger volume. So those are some of the reasons why gases occupy more or greater volume than liquids, or when water is in a gaseous state, it occupies a bigger volume than when it is in a liquid state. Let's go to Roman numeral 2 of part B. State two ways in which boiling differ from evaporation. So we shall say that boiling takes place throughout the entire liquid. Of course, evaporation only occurs on the liquid surface. So, but boiling will occur throughout the entire liquid. Then another difference is that boiling occurs at a specific temperature. We call it a boiling point. So for boiling to take place, it must occur at a boiling point or at a specific temperature. But evaporation takes place at any temperature or at different temperatures. Part C, water is replaced with 200 centimeter cubed of milk. The initial temperature of milk is 20 degrees Celsius and the boiling point of milk is 95.0 degrees Celsius. The milk starts to boil when 60,700 joules of thermal energy has been transferred to it. The density of milk is 1.03 grams per centimeter cubed. Calculate the value of the specific capacity of milk and give your answer to 3 significant figures. So let us first obtain the mass of milk. Sorry, let's get mass of the milk. Of course, mass is equal to density times volume, which would be equaling to 1.03 times volume, which is 200, and you'd be able to get mass as 206 grams. After getting it, we can use it in this formula, whereby quantity of heat or change in energy or energy transferred will be equal to M mass specific capacity times change in temperature. So we are going to substitute and say that 206 times specific capacity that we are looking for, then times change in temperature. So remember, the boiling point is 95.0, but originally it was at 20.0 degrees Celsius. So you'll be able to get, and already we have the change in energy. The energy supplied is given to us 60,700 joules is equal to 206 times specific capacity times 95 minus 20, that is 70. That is actually 75. Then you'll be able to get, you divide this by 206 times 75, divide by 206 times 75. So this one will go, and finally we shall have our specific capacity as 3.93. So we can write it here, 3.93 joules per gram 10 degrees Celsius. So this one means that we didn't convert our grams to kilogram. So the answer is supposed to be that. And we are supposed to write it to 3 significant figures, and those are the 3 significant figures. Number 5 is a number on light. Figure 5.1 shows a semi-circular transparent plastic block. A ray of light is incident normally on the curved surface of the block. The refractive index of the plastic is 1.5. Calculate the critical angle of the plastic. So from critical angle, we are supposed to use refractive index is equal to 1 divided by sine C, where C stands for critical angle. And already the refractive index is given to us as 1.5, which is equal to 1 divided by sine C. C is the critical angle that we are looking for. So you cross multiply, it will be 1.5 sine C is equal to 1 times 1. So finally you will have sine C is equal to 1 divided by 1.5. So C alone will be got from sine inverse of 1 divided by 1.5. So C is equal to 41.8 degrees. To two significant figures, you can write it as 42 degrees. Let's go to the second one. On figure 5.1, draw the path of the ray in the block and after the ray emerges from the block. So since this one is perpendicular, it is normal to the surface, it will not be diffracted. It will go straight. Then if you can draw the normal here, and then it is internally reflected. And then this is angle I, this is angle R. Make sure as you're drawing it, let the angle of incidence be equal to the angle of reflection. So let's continue to part B, which is in a full scale. They are asking us to draw the path of light in the block and after the ray emerges from the block. So here we are supposed to first of all determine the focal length of the lens. So we know we are seeing where F is, we are seeing the optical center. So this length in between here, this length, use a ruler and measure it. It is supposed to be the focal length. And when you measure very well, you're supposed to get 7.2 centimeters. Then they say on the same diagram, draw two rays from the object to locate the image and label the image as I. Of course, using the principles as we are going to draw ray diagrams. The first one is that the ray which is close, and parallel to the principal axis, this ray, of course we must use a ruler, must converge through F. However, you draw another F the other side. This F is 7.5. Also from here you measure 7.2 centimeters. So measure and also put another F. So this is where this ray will pass. So it will pass via. And for you, make sure that you become accurate. Use a ruler and become very, very accurate. So I'm going to sketch it for you and then you use. So let's say this is F, and then, but let us see, put it slightly in front, like here. This is F. So you draw the ray through F, and there must be a straight line. Then another thing is that a ray through the center of the lens, which is the optical center, should not be deflected. So it should go through straight, like this. So these two rays, they are going to, you extend them or you prolong them backwards. But of course, make sure that you are using a what? You are using a ruler. Don't be like me. So use a ruler, prolong them backwards, extend them. And where the two meet, so they meet here, and then that will be the new position of the what? That will be the position of the image. So the image will be produced behind. So simply prolong the rays, and then where they meet, that's where the image will be formed. Part C, that is an eye defect. Figure 5.3 shows a simplified diagram of an eye with rays from a distant object and a path of the ray incident the eye of a person with a short sight. So this is an eye defect called short-sightedness, where the image is formed before reaching the what? The retina. So they want us to Draw an additional lens outside the eye to collect the short-sightedness and show how the pass of the ray inside the eye. So we collect it using a concave lens or a diverging lens, and of course we have the rays coming. There is a first ray in the middle, which is the principal axis for it to continue. So this is principal axis. Then of course when rays happen to reach on a diverging lens, they will diverge a bit. The rays will happen to diverge a bit. When you look at these rays, they have diverged. Then when they reach on this lens of the eye, they will converge. So they will have to converge to the actual, which is actually here. So that is the way you can draw them. But for you, of course, you have to use the what? You have to use the ruler. Let us continue. Number 6. Sound waves have compression and refactions. Explain what is meant by compression and refaction. So we are going to say that compression, these are regions. Compression is a region. It's a region where particles are closer. Or you can even say that a region where there is greater pressure. Again, rarefaction is a region where particles are far apart. Then in terms of pressure, you can say it can be a region. It's a region where there is lower pressure. So that is another definition. Any of the two can work for you. We can see light from the sun, that is part B, but we cannot hear any sound from it. State the reason for this. So we can say that in space there is no material medium, e.g. air, liquid, even solid, solid. So for sound to be what? For sound to be transmitted. For sound to pass through. You know very well that sound requires a material medium for its propagation or for its travel. And in space there is no what? In space there is no that material medium. It's just a vacuum. And sound cannot what? Cannot travel through vacuum. But for light is okay because light does not need any material medium. So for it can just move. Or you can even say that light doesn't need Light doesn't need any material medium. So in other words, for it can just move. But for sound, there must be a material medium for its propagation or for its movement, and which is not in space. Part C, during a thunderstorm, an observer sees the lightning almost immediately, but hears the sound of the thunder several seconds later. The thunder and lightning are produced at the same time. The sound of the thunder is 9.0 seconds. The light is seen. After lightning is seen, the speed of sound in air is 340 meters per second. Calculate the distance from the thunderstorm to the observer. Of course, we're given time, which is 9.0 seconds. We have got the velocity, sound in air, which is 340. So we shall first of all use the formula that distance is equal to speed or velocity times time, which is equal to 340 times 9, and finally we shall get our distance at 3060. So it will be, you can even write it to two significant figures, which is 310 meters. So that is the distance moved. Let us have part D. In a lightning strike, there is a current of 3.0 exponent 4 ampere for 48 milliseconds. Calculate the charge that flow. So we already know the current, which is 3.0 times 10 power 4 amperes. Then from that, we also have the time taken, which is 48 millisecond, that is times 10 power negative 3 seconds. And we know that charge is equal to current times time, which is equal to 3.0 exponent 4 times 8 exponent negative 3. And we are going to get 1440 coulombs. But two significant figures, you can write it as 1400 sorry, let me bring it back. So you can write it as 1000 400 coulombs. So here it will be 1400 coulombs. Let us go to another number. Define potential difference. So we are going to define potential difference as the work done. This is the work done. This is the work done. In moving one coulomb of charge from one point to another, from one point to another. Then state the equation which defines electromotive force E. So E is equal to work done. E is supposed to be work done. Work over charge. Work over charge, which is the same as W out of charge. So that is the equation which defines electromotive force. Then when we continue, we are given a question which requires a calculation. The EMF of the battery is 9.0 V. The battery is in a circuit. Calculate the work done by the battery when it moves a charge of 30 coulombs. So we have 30 coulombs in a complete circuit. So what you have to do, we know that EMF is equal to work done out of charge. We have the charge, we have the EMF, we are looking for the work done. So of course work done is equal to EMF times charge. So we have the EMF, which is 9.0, we have the charge, which is 30, and should be able to get the work done as 270 joules. So this is 270 joules. Part C, the circuit consists of a DC power supply, a lamp, and a thermistor. Draw the circuit diagram of these components connected in series. So let's have the DC supply. I can even make it a battery. Then there is a lamp here. That's a symbol for a lamp. Then we can have a switch. However, since it is not asked to us, so we have the thermistor here. And then can have a switch here. So that is a circuit diagram. So we have batteries. When there are more than one, you can call them batteries or battery. Actually here you can say battery. To be more clear, you can say battery. Then this is a lamp, and then this is a thermistor. So those are the components connected in series. Let's go to number 2. Explain what happens in the circuit you have drawn when the temperature of the thermistor is increased. So when the temperature increases, the resistance of the thermistor decrease. But of course, when the resistance decreases, more current, when the resistance decreases, of course, more current flows. More current will flow in the circuit. More current will flow in the lamp and in the lamp more current flow in the lamp. More current flows in the lamp. Flows in the lamp and becomes very bright. Okay, let's continue. We're having a coil between the magnetic field. So the question is asking us, determine the direction of movement of side AB. So this is side AB here. How will it move relative to the plane of the coil? So when you use Fleming's left-hand rule and see the direction of motion, because you have the direction of current is going like this, you have the direction of the field goes in that direction. So eventually the direction of the coil will be downward, so the coil will go down like this. So you can say it will move downwards. It means if it goes downwards, this side goes up. So the direction O can be, can say, anti-clockwise, and clockwise direction. That one can also work, and clockwise direction. Explain how you can determine the direction in A. So you can use by using Fleming's left-hand rule, whereby in Fleming's left-hand rule, the thumb points in the direction of motion. So the thumb will point in the direction of motion. The first finger, of course, it is direction of the field, that is from north to south, and the second finger in the direction of current. See, state and explain what happens to the coil as it reaches the vertical position. So the coil will vibrate. The coil vibrates. In other words, in the vertical position, the current supply is cut off. Since the split rings, they are not directly connected to the what? To the current circuit. So the current is cut off, and then the coil will vibrate. By the way, it will continue in the motion due to inertia, because it has been in motion, so it will continue moving. So you can also say that the current is cut off since the split rings are not connected to the circuit, So you can see that the current will be cut off. Also, the coil will continue. The coil will just continue moving, will continue in motion due to inertia. Continue in motion due to inertia. The movement of the coil is not because the current is flowing through the coil and the force of motion is generated, but this motion is due to continued motion due to inertia. Because it has been in motion, so it will continue moving due to inertia. Let's go to part C. Explain the effect of the split rings, commutators, and the brushes on the action of the motor. So to operate a motor, split ring, commutator, and brushes are added to the part as shown in that figure. Explain the effect of the split ring, commutator, and the brushes on the action of the motor. So the first one is that commutators or split rings reverses the current. Reverse the current when the coil is at right angles to the magnetic field. Number 2, brushes. The brushes provide a contact between the coil and the power supply. So those are the uses of the brushes and the split ring commutator. Let's go to another number. A nuclear power station has a reactor where controlled nuclear fission of uranium-235 takes place. So explain what is meant by nuclear fusion. So nuclear fission can be defined as, or you can say, as this is the splitting. Splitting of a large unstable nuclei, actually nucleus, into two stable lighter nuclei. This is a nuclei. There are two, which is a plural for nucleus. So let's go to Roman numeral 2. State one advantage and one disadvantage of generating electric power in a nuclear power station compared with electric power generated using turbines. So number 1 is that this one does not cause air pollution. That is number 1. Number 2 is that produces a large amount of energy. All these advantages produces a large amount of energy. Then the disadvantage let me just fuse it here. Does not cause air pollution, and also another advantage can be produces a large amount of energy. Produces large amount of energy. And lastly, you can say that a disadvantage can be it's not renewable. It's not renewable. Once it is used, you cannot get it again. Once it is done, then you cannot get it again. Part B, deuterium is an isotope of hydrogen with 1 proton and 1 neutron. Nuclear fusion occurs when 2 nuclei of deuterium combine. So, an isotope of helium and a neutron are formed. Use nuclear notation to write down the nuclear equation for this reaction. So it will be 2 mass number, 1 proton plus 2. Then it will give you 3 mass number, 2, then plus 1, 0. Make sure that the atomic number is balancing with the mass number. So you see that mass number is 3 plus 1, which is 4, and the atomic number is 2 plus 0, that is 2. And of course, when you compare in both sides, the mass number is 4, and the atomic number is also 2. Make sure that they are balancing. Number 10, which is our last number. The time taken for the Mars to orbit the Sun is 690 Earth days. The average orbital radius of Mars is 2.28 exponent 8 kilometers on Earth. An Earth day is 24 hours. Calculate the average orbital speed of Mars in actually they want it is in kilometer per second. So we know that orbital speed v is equal to circumference over period or over time taken, so which will be equaling to 2 pi times the orbital radius, which is given to us as 2.28 times 10 power 8 kilometers over time taken. Of course, we want our answer in kilometer per second, so we have to go as far as a second. So we shall have 690 times 24 hours in a day. In a day, 24 hours. There are 60 minutes in an hour, and there are 60 seconds in a what? In a minute. So finally, we shall get 24.029. When you can record it to possibly 3 or 4 significant figures, you'll have it as 24.03 kilometer per second. State the shape of the orbits of the planets. So the shape is supposed to be elliptical. Elliptical is the shape. Light from a distant galaxy is red shifted. Explain what is meant by redshift. This means it can mean wavelength. It means wavelength increases. Can also, we can say, change of the wavelength. Change of the wavelength. Change of the can mean change of the wavelength. Change of the wavelength. Lastly, State the quantity that the redshift of the galaxy is used to calculate. So it calculates velocity, or you can call it speed, that the galaxy is moving, the speed that the galaxy is moving away from the Earth. The speed, or you can use velocity, that the galaxy is moving away from the Earth. Thank you, learners, for being with me up to the end of this paper. And I want to encourage you to click on the subscription button, and after you click on the bell, so that whenever I post anything, you are able to receive it, or you receive a notification. I wish you the best, and I remain Teacher Stephen. Bye bye.